Okay, let us start. What I want to do is this Couette flow, I want to do it thoroughly. I like this, I assume hopefully you will also like this, because it is a complete very this can be done completely in the class, starting from the beginning to the end by hand. But that is not the only thing, there are some very nice concepts which come out of it, and this is one of the very few, as always we say, one of the very few exact solutions of the Navier-Stokes equations. Navier-Stokes equations are very complex with certain assumptions, definitely, but when we do this, also the flow is very simple, one of the simplest flows. Actually I would say this is the simplest problem in convection. It is a convection problem, it is the simplest in convection. You will see why it is so. You will actually do it along with me. I want you to do step by step, starting from the beginning. So today and tomorrow we will completely allot this. I will ask you to do something at home later. Okay, let us start. This is a parallel plate problem basically. Usually we divide the problems, this is a flat plate problem, pipe problem, square duct problem, curved bluff bodies. This is a parallel plate problem, point number 1. We call it in literature Couette flow problem, C-O-U-E-T-T-E, Couette flow problem. So that is what in particular we are talking about a Couette. This was a this is called Couette flow in literature. It was I think it was a French person, his name has been given. We have tried what was his contribution, it is nothing great actually, but it is referred to as a Couette flow. It has a certain practical application which may look very trivial, but it gives you a lot of information. That is why I like this, and hopefully you will like it. So I will also add a adjective to this. This is called plain or simple Couette problem. Now, objective of this is, as usual, to obtain velocity and temperature profiles, and getting the profiles is not the end of the solution. We would like to estimate, calculate rate of heat transfer. I will say in the system now, then we will see what it is, and then study this a little further, study the results and see what comes out of it. This also involves interpretation. Just getting the profiles of heat transfer is not enough. Then you have to look at the consequences of that, study a little bit, analyze. When you do this for any problem, then you know how to use it. So simply solving a mathematical model through a code, you will give the nice profiles. That's not the end of it. You have to know the results, interpret them, study them, and then say, okay. Study them means, you know, what happens if I change this? What happens if I change that? Why is this happening? Where is this possibly used? How can I control the flow? How can I control the heat transfer? That should come from the results part of it. So a complete solution involves interpretation and study also always, and there is no end to that. Now we will start. What is the very first step? We will do it in steps when you want to study a problem, in any problem, but here we are talking about convection. What is it? I have simply stated a overall title I have given, parallel plate problem. You must have an idea what it is. We will write it down, and it is called a plain or a simple Couette flow. When I give that adjective, you should immediately think, oh, there should be something other kind of a Couette flow. more complex, not so plain, not so simple, obviously. We will see. Now, in any convection problem, conduction, radiation, whatever it is, what is the first, when you want to study a problem, what is the first thing that you do in our scientific methodology of, not the experimental part, scientifically? Okay, I will give you we are actually going to model this, let us say. So, what is the first thing that you write? You should, pardon me? Hey, come friend here, why are you sitting at the infinity? It is like y tending to infinity there. The y equal to 0 is vacant here. Tremendous resistance, heavy shear stress here. Okay, you want to be free, or all free stream people. Okay, tell me now. That's all. I will not say anything more about it. What is the first thing that you do? You have to do. What is it? Geometry. Can you give me a different, slightly better term? Boundary conditions will come later. Exactly. That's why I want to clear it out here. How can you talk about boundary conditions without even talking about the equations? But before you talk about the equation, something else has to be known clearly, which we, for clarity, we write down. Diagram. You said what? Geometry, flow conditions. Can you combine all this and give one? Pardon me? What is it? Say that it's okay. Assumptions will come later. We will do that. I am now trying to identify and write down all these things are correct. Geometry, you said, diagram, flow, description. Okay, fine. In what you want it to write in words, or you want to formulation? Correct, formulation. Okay, I'll just want to use the word a dash model. First we should have mathematical model. That's exactly the point. It will come later. Okay. So now comes the diagram, geometry you are talking about. We said parallel plates, right? Parallel plates. Two parallel plates. Now we will define this plate. These are large plates. In our heat transfer, there are some words which give you some ideas which you should use. Large. Now what do you mean by plate being large? Plate is large. What meaning do you make out of it? Okay. So very good. Very long you in one particular direction. The other one is very long is length. The other one is okay. This is okay. Now I can also add this is thin. Why do we say it's a thin plate? We should actually, whenever we talk about solid, usually we say thin plate because there could be thick plates also. What would be the difference between these two in terms of what you should consider in heat transfer? Then you have to consider the conduction in the thick plate also. That becomes a conjugate problem kind of a thing. Thin means the entire that thickness is at one temperature. You can take it like that. Now very long and very wide. So let us now have the coordinate system x, y. For me this is always in convection x and y, these are the directions. Even if I go to free convection, x along the surface or in the direction of the flow, y perpendicular. X, y, now I will also write this z. This is for the flow. Now if you take that in terms of the plate, that means this x is very long. So this is very long means it is infinity. These are all very simple things. I am trying to make it clear to myself and to you, so that how you can write it down. X is infinity. Now we will not make y infinity, we will make z infinity. Z is perpendicular to the plane of the board. So the example I usually give is this is the top plate, the roof, this is the bottom plate, and they are extending in two directions infinite. This is why this is a parallel plate problem. Actually this is a duct enclosure problem. If you take this room, is an enclosure problem, 4 walls and top and bottom, but remove these 4 walls, you get the parallel plate problem. And therefore in the z direction also it is. Now this is why I have to obviously say what is this. Let us say it is, they are displaced, there is a gap of L. We will not specify at this point how much it is, we will just put it as L. Now where is the flow? He said we have to define the flow, where is the flow? This is a very peculiar problem. Usually what you would do, you put 2 parallel plates and then say flow is coming from this side. No. Now I will say, first of all, what is there in between these 2 plates? So now let us say there is some fluid, we won't even say air or water. The moment I say fluid, so what is the number we are specifying? So we say there is a fluid number, there is a fluid, it has a certain Prandtl number, meaning it has certain properties. Pressure and temperature come into the picture, mu Cp by K, mu function of temperature, Cp function of pressure temperature, probably K function of temperature. So pressure and temperature is taken care of. That gives you the fluid. So if it is if you say it is 1, it is a gas, if it is 4 or 5 it is water up to 10, 20, if it is hundreds and thousands it is oil, 40, 50,000 is heavy oil, 0.01, 0.01 is liquid metal, that is fixed. Now, so there are 2 parallel plates. Now we will define a little bit further what are these plates. So now I am not saying there is a flow here. How would then a flow exist? Now I say this top plate is moving. Bottom plate, you can, in convection you can have any kind of geometries and situations and you can try to solve them. I will say the bottom is fixed. This hatching for me is either it is a fixed plate or it is insulated. In this particular case I am saying it is flat plate, fixed plate. And there are 2 plates parallel to each other displaced at a distance L. So we call this the bottom plate, this is the top plate. So the bottom plate is fixed, the top plate is moving, then I have to prescribe something, it is moving with a velocity u1. 1 refers to the top plate, 0 this refers to the bottom plate, subscripts later. Now anything else to be defined? I am now completing the physical model basically. You have the diagram, you have the flow. Flow means now I am saying in steady state, by the way, we will define it again. The top plate is moving, so it is not fixed, it is not insulated. Bottom plate is fixed at this point in time. For me to have heat transfer, one would think there should be a temperature difference. So I will say this is at a temperature T1, this is at temperature T0. So now you see we have prescribed the velocities and the temperatures. Anything else required for us to continue? This physical model is complete now. 2 plates, large, x infinity, z infinity, displaced at y, thin plates. There is no imposed flow, bottom plate is fixed, top plate is moving. One would think therefore there is a flow is induced. Induced is different from imposed for me. Imposed would be I put a fan here or a compressor, that would be inducing the imposing the flow. But as long as you understand, you can use whatever word you want. Bottom plate fixed, top plate moving in the x direction. This is very important also for us. So it is a Cartesian, and we have selected the Cartesian coordinate system. Okay. Now what kind of a fluid here? Now we will go one step ahead. What kind of a fluid we would like to have here? We can't, of course, I will prescribe that, you will prescribe. We will say this is a Newtonian fluid. See, many a time we take all this for granted. I am trying to make it a little bit more. So don't think it is so simple, you know, it's known. Sometimes you make mistakes here also. So Newtonian fluid, meaning it follows the Newton's law of viscosity, tau equal to mu del u by del y. It's a Newtonian fluid. This is the fluid, number 1. 2, what kind of a flow we will now assume? We will now say it is incompressible. Is a fluid, do you refer compressibility, incompressible to the fluid or a fluid flow? Do you call it an incompressible fluid or incompressible fluid flow? Compressible fluid, compressible fluid flow. Think about it. We will now say it is incompressible. This, so I am prescribing, this is not an assumption at this point. I am saying I want to study this, incompressible. What else in terms of flow, what else I have to say? Huh? Okay, steady. That's enough? Is that enough? A point from the coordinate system, what is it that I have to write? 1, 2, 3. So you have to say, let us write down. Then what else? Huh? Very good. Something from the point of view of properties. Homogeneous we don't use it. No, that term we don't use, but properties. Either the properties are x or they are y. You decide at the initial point. All your equations, when you write, this point is very important because the type of equations will change according to this. What is that? So the properties for our problem are considered as, I want the answers from you, therefore I want to have this interaction. It doesn't matter if it takes time. The properties are either, actually there is a very important assumption, that is how you write your u del u, all equations you write, only then you can write those equations in that form. I will give you a del u, I will come to that continuum, yeah. In this particular case, constant we mean with respect to the temperature and pressure, not with respect to time. That is one way of doing it. With respect to time, the properties will change only if the pressure temperature changes with time. We will leave it aside. This constant property is not a very nice terminology from English point of view, but that is used in literature. Constant with respect to temperature and pressure. So properties won't change is what we have kind of. Now you see, this is the beauty and complexity of convection. There are so many things that you have to specify. When you do this and then get the mathematical equation and then put the boundary conditions, for every one boundary condition and this combination you will have one solution. You change one boundary condition, you have a different solution. Keep the boundary condition same, change one term in the mathematical equation, solution are different. And those equations depend upon this. So if it is not incompressible, you have a whole set of new equations where the properties, the rho especially goes into the derivative. Steady, unsteady obviously you know, laminar turbulent obviously you know, 3D, 2D, 1D, single phase, two phase. So when you look at flat plate, Nusselt equal to 0.332, Reynolds half, Prandtl 1/3, all this must immediately compute. 2-dimensional, laminar, incompressible, constant property, Newtonian fluid of course, air, all this give you that solution. You change any one of these definitions of the problem, your 0.332 does not hold good. So you cannot simply say flat plate put 0.332 Reynolds half Prandtl. You should know what is behind that particular solution. Okay, this is the, yeah. So I would like to take this out. This is a very important boundary condition which we assume at the beginning. there is a difference between assuming and defining the problem. Constant property could be an assumption, but I am now trying to define. But this is I am defining the problem here. Then assumptions will come in about the situation, about the conditions. Then you simplify the equations. Okay. Now what I want you to do is for me this is the full physical model now. This is I am considering this problem. Diagram is one of the aspects. All these things you have to be very clear. If you are, it's better to write down always, so that you can proceed to the next step. So that is a physical model. So from physical model you graduate to what should you now get? Now the physical model is ready. So now we have to write down the math model. Math model consists of two things. What are these? Boundary conditions will come later. First, before the governing equations. Only boundary conditions. When you do this, the mathematical model is complete. So don't think mathematical. When I say don't think out of experience, I am saying mathematical model simply people write the equations and leave the boundary conditions to me. Only when you write the boundary conditions, looking at the proper the equations, how many boundary conditions, how many boundaries, how many conditions, so what is the order of the derivative, then only the problem is now complete. Hopefully it is now ready for the solution. Now, so we will now get the mathematical, you will get the mathematical model for this. What I want you to do is write down 3-dimensional, for this situation, the Navier-Stokes equations, complete Navier-Stokes equations. We have not talked about boundary layers here, we have not talked about boundary layer, make a difference. Write down the complete Navier-Stokes equations, continuity, x component, y component, z component, energy, no species, start. As and when you finish, you please tell me, I will write it down. Continuity equation, 3-dimensional, laminar, incompressible. Incompressible is very important here, constant property. Sir, give me the 3-dimensional continuity equation. What is it that you say? You are somehow jumping ahead, maybe I am a little slow. Give me the first 3-dimensional continuity equation for these conditions. What is it?
Dou u by dou x plus dou v by dou y plus dou y by dou w by dou z. 0.
If it were to be unsteady, what would it be?
Dou u by dou t.
Dou
Rho by dou t.
If it is incompressible, so this is also for incompressible, it is a unsteady state also, this is the equation. For unsteady you get only del rho by del t, in that term you do not get UVW, that is only the property variation. If it is incompressible, if it is compressible flow only, that will come in as a continuity equation. In incompressible flow, del rho by del t is 0. So del u by del x plus del v by del y plus del w by del z equal to 0 is the continuity equation for incompressible flow, steady or unsteady. Okay. Now x component, now we will write momentum, we will start giving numbers please. Momentum equation please, x component, dou u, okay, we will write it because although I have said here unsteady, steady, at this point we will say unsteady and then make it steady. Good. Okay, give me this please quickly. U dou u by dou x so yeah, equal to what? Minus plus no, you are right. Okay, I will say the x component of the body force, but I have divided every by rho. Write this for the y and the z components. Please completely write. Convective terms are inertia terms, pressure, body force and the viscous. Write for W also. Three components you have written. Now write the energy equation now. Can you tell me one by one terms? Energy, yeah, rho T by plus, yeah, this is very easy to write, u del T by del x, v del T by del y plus w del T by del z. You all pronounce it as dou. I always pronounce it as del. Okay, you understand? Okay, is equal to what now here? Alpha. This is the Graetz square T actually. Anything else? Write the complete energy equation for incompressible. Then we will make assumptions. Huh? Sometimes we write phi, sometimes mu phi. If you don't write mu phi and write phi, in the definition of phi would have included mu. Here that mu you can take out, take it away from that. Okay. Huh? Yeah. Thank you. Is that all? Anything else? There are actually two more terms. One is a compressibility term, but we have said incompressible. Otherwise, you should write the compressibility term. Beta comes into picture. Expansion coefficient. So write down Q triple prime by. So this is 2, 3. No. 2, 3, 4. No Blasius equation. Now actually you have to solve this set of equations, 3-dimensional. This is the complete Navier-Stokes equation now what we have written for this particular situation. Now we make, this can be done with a, of writing the boundary conditions of course for U, V, W, T, P and everything. Only on a big computer you can do this and not analytically. Even your approximate integral method may or may not work here. Almost definitely you have to go to a basically what we call the DNS, direct numerical simulation. But we will see it, we will avoid it. So tell me, we will make some simplifications now. This is step number 2A. Simplification. We have not yet completed the mathematical model. Now I will give you. Now this is a parallel plate example I am giving. Now if I want to consider the flow somewhere in the middle of this plate, in this portion. So, physically what would you how would you interpret, how do I ask this question? I want the flow, although I have talked about two plates, I want to talk about the flow only in this region. What am I implying actually when I say that? I am, what is it? No, I did not communicate the question properly. I am interested only in the flow between these two plates, but only here means now tell me what I am trying to neglect. Okay, let me put it the other way, give me a hint. I want only in this portion here, instead of taking the entire plate. That is why we have given the example, we have used the word large actually, now I am coming to that. When you say large plate, in the majority of the plate zone, what is it that you can neglect? Entry effects and once you, correct, once you, actually there is no entry here, there is no entry, but let us take it that way. Entry, when you say entry, another thing is exit on only on one side, on both sides, no, but there is no entry here, no exit. So, we would very correct. Now, we would say in the so called x direction we call this the ends of the plate, end, and in the other direction we call it the edge. So, there is a end, two ends and two edges. Now, we will say if I want to consider the flow only here, the effects at the entry and exit I may neglect. How do you neglect? Now, mathematically how do you neglect entry and exit effect on both sides? What would you say in terms of mathematical terms? I will write here, you came up with the right answer physically, no end effect means what? I have to give you a hint. What kind of derivative terms you can neglect? You neglect this. Then, so that I will say neglect. I will say no edge effects. What would you neglect? Dou by? That means, ladies and gentlemen, no ladies here. The flow is really three dimensional. In this box, for example, you know where? In those corners. That is a three dimensional corner. This is a two dimensional corner. Here you have the two flows, if there are flows, interacting to give you those two dimensional, three dimensional effects, especially three dimensional effects. But if you take somewhere here a simple flat plate, now you can take this as a flat plate. Flat plate need not be horizontal, flat plate can be vertical and then the flow can come here. In the majority of this area, if you leave out the leading edge as you have known and the trailing edge, you say those effects you can, but in a boundary layer flow you cannot do that. In fact, that flow at x equal to 0, that is a leading edge thing that creates a lot of problems actually, and especially in your numerical, if you are going to solve numerically, what is the condition that you are going to put at x equal to 0 is a big problem. Y equal to 0 is no problem, x equal to 0 what? That is a singularity situation there. Okay. No end effect, no edge effect. Now I will say one more thing, only G effect, only G as a body force. You know what this leads to. What are the other body forces? Yeah, then in an actual, yeah, that's good, but in our applications in mechanical engineering, for example, body force acts on every molecule of the volume. Surface forces act only on the surface, so pressure and viscous. The body force acts on every molecule. One is G. No, viscous is a surface. Pardon me?
Normal reactions.
No, that is also surface. Normal stresses. Normal and viscouses act only on the surface. I will give you a hint. a turbine. Go further ahead, the earth is rotating on its own axis and rotating around the sun. What forces come into picture? Coriolis forces. So electromagnetic forces, Coriolis forces, centrifugal, centripetal, all of them act on every particle, therefore they are called body forces. The body, the entire body, otherwise they are surface forces. So here we will take the simplest G and therefore it is a natural force G. Okay. Now as and when we go further we will make other simplifications. With this, can you now simplify this? We are now still doing the mathematical model. Please simplify this. See what equations do you get. Now get me 4 equations with all these assumptions that we have made. Take the first. Take the by the way, you are right, thank you. We also take steady, very nice. Start from the continuity equation, simplify it. No end effect, so what is it that can be neglected? No edge effect, there is no assumption on this. So the continuity equation now is del V by del Y equal to 0. Please write down. Right? Go to the x component please. So I will say del V by del Y equal to 0. Then x component del U by del x, del U by del Z. Now this is a problem, we will come back, del square by del x square, del Z square, this is not there. Now we will say del P by del x is 0 edge effect because we are not imposing the flow with a pressure difference from outside. The inertia terms and the viscous terms are taking care of each other, that is what is keeping the flow. So and also we are saying no edge effect, so all del by del x is cancelled. So steady state, now write down the expression now. What is the x component momentum? There is not a boundary layer thing, there are no boundary layer assumptions. This is Navier-Stokes equations with certain geometry, flow and some assumptions we have made, like no end effect, no edge effect. So what is this? Del square, give me the entire expression that you got here. V dou U by dou Y is equal to okay. Now before going further we will make a small thing. Now here look at the continuity equation, del V by del Y equal to 0. Okay, we will do it later, leave it, we will come back later. So this is 5, we will come back later, we will further simplify it. Then write down the Y component, this is very interesting. Same thing here, del V by del tau, del V by del V by del x will go, del V by del Z will go. Okay, we will invoke a boundary condition and do it. I wanted to write it later, but we will do that. Tell me the boundary conditions on V. At y equal to 0, please write down, at y equal to 0, what is V? Why? Why?
No penetration.
Huh?
No penetration.
No?
Penetration. No slip like this station.
V equal to 0, slip does not come under V for V. V equal to 0 is perpendicular to the plate. So for V equal to 0, what should be the assumption that we have to make or the condition that we have to specify?
Flow is in one extraction.
There are no perforations, so there is no V component, means it is a solid plate, it is an impermeable plate, please, that we should have written here. Actually I could have written right there. Now just so there is no V component, but is that right? Just because there is an impermeable plate, you think there is no V? There is another condition where for an impermeable plate there could be V. You are saying V, if it's there are holes and then you put in air or whatever the fluid, suction or blowing is not there, but I would like to state that V could be there even for my impermeable plate under certain conditions. You know this, you know the answer. I want you to give me, I will give you 2 minutes. Give me a physical situation. Natural convections also have an impermeable plate. There is no V component there, perpendicular to the impermeable plate, there is no V component. That V is at the wall, it is there in the boundary layer. At the wall we are talking about, at y equal to 0 we are talking about. Okay. You have a water body, our reservoirs, Madras reservoirs which do not have water, no, enough water. Then there is a flow over that, there is a wind. What happens? That is a solid surface actually, impermeable surface rather, water surface. But now there is a V component. That V component is actually evaporation that is occurring. Now can you go further and say something else to maybe at least definitely one other situation, 2 situations, maybe 1 situation. Evaporation is one, related to that something else. You see it all the time in your refrigerators. Yeah, there is a condensation, that is the boundary condition you have to use, there is a V there. So it's impermeable plate V equal to 0 because there is no blowing and suction, but also there is no V equal to 0 because there is no condensation or evaporation even with a solid plate. Okay. So now we will do that impermeable plate. On the other hand, can I use some other term for us to say V equal to 0, some other term, not evaporation, no boiling, no condensation, any other generally accepted term I can say no this thing. Okay, we will do that. So V equal to 0, we have not yet formulated the problem, but it is okay. Now take that V equal to 0 at the wall, both walls. Take this continuity equation you have written del V by del Y equal to 0. So what is the consequence of this? If you apply the boundary conditions on V for this, what is the consequence of that? Just look at that. V equal to 0 at the bottom plate, Y equal to 0, please write down. Y equal to L, also V equal to 0, dV by dy equal to 0. Therefore, what is the conclusion out of this? V equal to 0 where? Everywhere. V equal to 0 everywhere, there is no V component at all. Because at y equal to 0, V equal to 0, actually y equal to 0 I should not write V0, we should say VW equal to 0. And y tending y equal to L also VW equal to 0, and this equation together, this component continuity equation and the boundary conditions tell you V is 0 everywhere. This is a very important physical interpretation. V equal to 0 everywhere. Now use this for the y component. See what happens to the equation. Here what happens? Sorry, use it even for the x component first. V equal to 0. So what is the x component equation now? Please. Dou square. That's it. There is momentum equation. What have you done in one shot? All the convective terms are gone. Viscosity is there, but because of our this new del square u by del y square equal to 0 actually, but now it has come down to d square u by, actually del square u by del y square, del v by del y, I want you to do another thing. It is only in the y direction that every equation is coming along now. This is del v by del y, del square u by del y square. You can as well write this as change the dou to, that is it. So now it is coming into an ordinary differential equation. Here see how we have simplified that entire momentum x component. Now go to the y component. Go to the y component. I had to do that v equal to 0 everywhere so that you can simplify this. But what remains here in the y component? There is something still remaining. Pressure and now, so write down that expression and tell me a solution for this. Just write down the y component and the solution is hidden there. Fy is only body force is g. So what is that Fy? Y is the y component of the body force. What is the force there? Yeah, give me the variables there in terms of the variables. So rho g, and in what direction is rho g? No, y direction, upward or downward. So it should be rho g prefixed with a. So now get the equation and automatically you will get the solution. Find out what it is. 1 by rho dp by dy equal to rho g. So what is the solution for that? Delta p equal to what is that equation? That is it, that is the solution. Y component is delta p means within the boundary layer, within the fluid layer, p minus p naught or whatever you is equal to minus rho g h, rho g y. There is no more solution required, that is the solution, minus rho g y. So component has given its own, the momentum equation has given its own solution, you do not have to solve it anymore. So delta p equal to minus rho g, actually you will get it as y. So it simply says very correctly also minus actually, so it is reducing, P2 minus P1 is reducing, means P2 as you move away from the surface the pressure is reducing. Now look at the z component very quickly. Yeah, you have it. Give me the z component equation, 1050 you have to go. Z component del w by del tau 0, all del by del x's, all del by del z's. So what is it? What is the equation? You have an equation still. What is that? Dou square, right? Huh? Now invoke again the boundary condition. What is W at the wall? What is bottom wall? What is W at the top? At y equal to 0, W equal to 0. At y equal to L, W is 0. So W is 0. Complete the sentence everywhere. Quickly do the energy equation, can you do it? It is 1051. I have written down here, so we will do this. Del T by del tau is 0, del T by del x is 0, V is 0 here, del T by del z is 0, W is 0, del square T by del x square is 0, del square T by del z square is 0, and now we will put one more condition here, no internal heat generation, we will now add, so that goes off. Phi is full of derivatives. Can you write down? You know it? You must have it somewhere at the back. Del u by del x whole square plus del v by del y whole square plus del w by del z whole square multiplied by 2. That is single terms all squares, then two terms come into picture. You have it, please write down, and then invoke this no edge effect, no side effect. Simply I will give that to you as a small exercise, do that and obtain the energy equation, all that you have written here, as simply d square T by dy square plus mu by k du by du whole square. Where is this du by dy whole square coming from? From the viscous dissipation. Everything else cancels out there. I have already put d, I should not have done it, but I have already mentioned. You will see that all the derivatives are only function of y, therefore instead of dou you can simply make them into ODEs. So you have d square dv by dy equal to 0, d square u by dy square equal to 0, this is the solution already, this is d square w by dy square equal to 0, d square T by dy square plus mu by k du by dy whole square equal to 0. We never made an assumption, any other assumption with viscous dissipation. I have maintained that term, that is very important, from that you will get a lot. Now what is it there, therefore you have to solve? This is already taken care of, this is solution v equal to 0 everywhere, this is v equal to 0 everywhere, w equal to 0 everywhere, this is already solved. So finally, ladies and gentlemen, the only two equations you have to solve is d square u by dy square equal to 0, d square T by dy square plus mu by k du by dy whole square equal to 0. Please put the boundary conditions at y equal to 0 for u, v and t. At y equal to 0, t is t naught. Please, okay. Now this is completed the equations. The mathematical model is not complete till you write the boundary conditions. Please write the boundary conditions. At y equal to 0, u is 0, v is 0. We have given the reason why it is so, and w is 0. T equal to t naught. Y equal to L. U equal to u1. Now what is this condition called? I did not mention, you know that. When I put y equal to 0, u equal to 0 and y equal to L, u equal to u1, what is the condition I am invoking? Physical condition. What is it called? No slip condition. This is where all the problem starts for us. If there were to be slip, it would have been wonderful, then that would have been ideal fluid, Duhamels principle would have worked. The real fluid, the problem is this is creating the entire boundary layer problems later, that one condition. Then what about the temperature? Y equal to 0, T equal to T naught, y equal to L, T equal to T1. What is this condition called? The other one was no slip condition. What is this condition called? No, we have taken it to be isothermal, not isothermal plates. Yeah, I did not mention, please write down isothermal plates. That is a one boundary condition that we have given. I am talking about writing down y equal to 0, T equal to T0 and y equal to L, T equal to T1 corresponding to no slip condition. There is a name for it. There is no slip means it is attached, otherwise it was slipped. Now temperature, in a very similar way we use another word. Okay, I will tell you. Perfect contact is very fine. Perfect contact condition you can call it, very nice. So we also call it as no temperature jump condition. Perfect contact is very fine, no problem. Okay. Now when you write all these boundary conditions, these two equations, ladies and gentlemen, you have now completed the mathematical model. We have to go for the step 4, which is the solution. I will do it tomorrow, but I want you to solve the momentum equation, there is no problem. Try to, from the momentum equation solution, try to solve the energy equation. We will do it tomorrow. We will finish it, and I want to calculate the heat transfers tomorrow. Okay. Thank you very much.